Alright, so let us have a look at overfitting in neural networks. We will briefly revisit the problem of overfitting and how it relates to the bias-variance trade-off, and then we talk about regularization, revisiting some of the standard techniques that you know from business analytics and data science, and afterwards examining some new techniques that are used specifically in the scope of training neural networks. So let's go. As I said, we will start with a brief reminder of what overfitting is about. So we are in the scope of supervised machine learning, where we train our analytical models in such a way that we minimize the loss over the training data. And then, depending what type of problem we face, in regression, we would typically measure loss by means of the squared error loss. In classification, we would use cross entropy. But in general, minimizing the loss or maximizing the accuracy of our model is what we are aiming at during training. At least this is how I used to present it, but if we think very carefully, we start to realize that this loss minimization is only a proxy of our real goal. In supervised learning, our real goal, our focus of interest, is maximizing the accuracy of our forecasts or the accuracy of our detection. If we build a system to do image recognition or something alike. So what really matters is the model accuracy in the deployment stage. When we deploy the model, when we put it into production, and when the model is fed new data that comes in every now and then, this is the point in time where model accuracy is really important. And I put a few examples here. For example, if we think about e-commerce and we developed a neural network to predict whether a shop visitor, the visitor of an e-shop, converts by, for example, making a purchase, then what we really care about is that this conversion model is accurate in classifying all the surfers that visit our website. Or for a financial institution, a credit approval model, it has to classify incoming applications. And what really matters is that these classification or these credit scores are accurate for all the applications that come in. And or for a tweet sentiment classifier likewise, you would want this classifier to accurately classify the sentiment of any tweet that comes in. So the bottom line message here really is that the testing stage or the deployment stage, when the model is performing its task in the environment, this is when accuracy really matters, as opposed to minimizing the loss over the training sample. And it's really crucial that you distinguish these two stages, model training and model application or the deployment or production stage. Maybe production stage is a good way to refer to this. And it may be that we build a model, we train a model, and we find that our model does very well on the training data, but that it in fact does so well on the training data that when we put it into production, its performance decreases substantially. And that generally is a sign of overfitting. A model that performs very well on the training data, but performs very poor, or at least much worse, on testing data that it has not been trained on, that is a sign of overfitting. And the origin of overfitting, if you wonder why might it be that a model is very accurate on your training sample, but rather poor on your test data, Why might that be? The origin can typically be traced back to the model during training, capturing not only the inherent structure in the data, the true relationship between the features and the target variable, but the model also capturing some parts of the random noise that any type of training data sample will typically embody. And this is why the model might then predict inaccurately when you when you put it into production, when you let it classify or predict novel data points. It performs poorly because it has learned to also fit the noise in the training sample, and by definition, noise is random. So trying to put forward these noise patterns the model picked up during training to the production stage, to the test set, this will not work. And that is what these pictures are meant to resemble. We have a classification problem shown in the upper panel and a regression problem shown in the lower panel. And in both settings, classification and regression, we have a true relationship in our data between the covariance x, between the features x and our target y, that is moderately non-linear. And then on the very left-hand side, you see a linear model that tries to solve the classification or the regression task. And of course, it fails because the true structure in the data is non-linear. And a linear model cannot accommodate this non-linear pattern. And then on the right-hand side, you see a very complicated model that basically solves the training task without making a single error. In the classification case, you see the class boundary to separate all the red crosses from the blue dots with perfection. All the crosses are on one side of the boundary and all the blue dots are on the other side of the boundary. So there is zero error. And the same is true for our regression example, where every single one of the blue data points basically is fit by our highly complicated regression function. So as far as the training set is concerned, the performance of our model is perfect. And these models, just by looking at the boundary and how the boundary between the classes or how the regression function looks very complicated, we can imagine that if we add some more data to the picture, if we add some test data points to the picture, let me try that. Looking at the example, I would believe that considering classification, that the relationship would somehow follow between x and y, somehow follow a square function or something like that. So it's easy to imagine that a test data point in the classification example might be here. Oops, sorry, my pen's not working. So this could be a test data point. Let's add some more test data points. Well, maybe another one here, another one here. And these test data points that I am adding here, I hope you agree, they still agree very much with the overall pattern that we see in the data, how the crosses and the dots distribute. So likewise, here might be another dot, and probably here, which is okay, but maybe also here. Judging by the overall pattern that we visually observe, the new data that I added is quite plausible. And you see how our model does not predict this data accurately anymore. And this would be an example of the overfitting problem. Good performance on training, bad performance in test. Probably it's even worse in the regression example, where we would believe the points coming from some U-shaped function. So very likely we might see a data point over here. Whereas our regression function would predict a value of that. And you see this large residual here, if this were a test point. Also, this point down here, I'm highlighting this point, which occurred in the training sample, it looks rather strange, judging by the overall pattern. It would be more likely, so let's get rid of this point, it would be quite likely to see some data over here, I believe, right? And see how bad our regression is for that data point. So very high error that we get. And this is exactly because our regression function is so much geared to the training data that it fails when test data is added that follows the same overall pattern of the training sample, but clearly does not exhibit the same type of noise. And the better picture would be the middle one. If we add some plausible test data to the middle picture, that still looks quite good. Of course, our regression function will never classify, it will never hit these test points with 100% precision, but it's near to them, right? So it does a very good job, or a fairly good job, in predicting these data points. The function would continue like that. So, well, we still have some residual here for this data point, but overall, we capture the true pattern much better. And overall, we would observe much lower error if we use the model shown in the middle, both for classification and for regression. And comparing these models, the middle one is not as simple as the linear model on the left, but it's not too complicated either. And finding such a balance between complexity or finding the right amount of complexity, that's really what matters in supervised learning. And the problem we can also look at this problem from the perspective of the bias variance trade-off that you should know from your statistics courses, a trade-off between bias and variance. In a nutshell, there are two roots that cause models to fail, or that contribute to models having some error. And these two roots, these two sources of evil, if you wish, are bias and variance. And you can show that for a predictive model, its error, and more specifically, its generalization error. I think I haven't formally introduced this term, generalization error. This means the generalization error is the error that you would expect on novel data on the test set, or when you apply your model to the underlying population. So it's an expectation of the true error of the model. So in this error, but also for the training sample, is a function of bias and variance. And the plot that you see here is a intuitive way to visualize the trade-off between bias and variance. So first of all, let's complete the plot. Here on the y-axis, we have model error. Let me try to write that down. So this is the error. And we have capacity on the x-axis. That deserves a little bit of explanation. Capacity means how powerful is my model. A linear model, for example, has little capacity. It cannot capture complicated relationships between the features and the target variable. It just can't, because it is restricted to a linear and additive relationship between x and y. So a linear model has limited capacity. Whereas a highly complicated neural network, for example, you can prove that such a neural network can approximate pretty much any nonlinear function, no matter how complicated it is, to arbitrary degree of accuracy. So it can cope with pretty much any situation in data, and therefore a neural network has high capacity. Or sometimes that's called, a term I like, that's also called the expressive power of the model. Expressive power. How powerful is our model to express complicated relationships? And then we see this pattern that the more complicated or more powerful our model is, the more capacity it has, the lower the bias. You see bias reducing monotonically with capacity. So that is good news. Low bias means low error. Now, there is also bad news. The more capacity a model has, the more complicated it is, the more variance it typically exhibits. And since variance is just another contributor of error, the overall error, which is a function of both bias and variance, the red line here, it will first of all start to decrease with model capacity due to the beneficial effect of low bias. But the more complicated our model gets, the more capacity it has, at some point the reduction in bias levels off. Whereas the effect on variance, the detrimental effect of the variance, at some point just dominates. And this is where the generalization error starts to increase again. So there is some sweet spot here where the capacity of our model is optimal, where you have found an optimal trade-off between bias and variance. And just to make sure, don't get fooled by this picture. The optimal trade-off between bias and variance, it's not necessarily where the two lines crosses here, right? In general, you do have on the left-hand side of this picture, you have an area or a zone where your model is not complicated enough, where you lack the capacity to express the true relationship in your data. And that is called underfitting. And then, on the other hand, there is overfitting, where your model is so complicated that it has very low bias, but is highly variable. The forecasts exhibit a high amount of variance. If you train a model on a different sample, on a different training sample, you get a much different model. So the models that you get and the forecasts that these models produce vary a lot when you train them on different training samples. That is a way to think about variance. And again, then there is this sweet spot where the balance between bias and variance is just right, and where the model does neither underfit nor does it overfit. And then mathematically, you can really decompose the error of the model. More specifically, here we think about a regression model where we measure error using least square loss, or the squared error loss function. Right? You see how this is the squared error loss here. And for this specific type of loss function, it's relatively straightforward to prove this relationship, how it is a function of bias and variance. And you see that we look at the expectation of the squared error, how it developed in expectation. And for this loss function, we can then show how this is a function of bias squared plus variance plus some idiosyncratic noise, some residual noise that we cannot avoid. That just exists, right? But for other type of loss function, cross-entropy loss, for example, it's much harder to show and to prove this functional dependence of the generalization error on bias and variance. I won't go there. You can read up some papers if you wish, but in general, what remains true is that you have these two drivers of the error. No matter what loss function you're using, you have bias and variance. These two error drivers which are in conflict, where there is a trade-off. And what I like, and maybe you have seen that before, is this illustration of bias and variance, where you look just at a bull's eye and imagine a shooter trying to hit the target, where the picture, which if we now imagine somebody shooting darts or an arrow or whatever on this bull's eye here, low bias, low variance would mean that you are always on spot. So this would be an archer. Let's say we shoot arrows. This would be an archer with low bias and low variance. And conversely, because she's always on spot, right? If we have an archer who has low bias but high variance, this means you do get it right on average, but, well, your shots, they vary a lot. So that might be something like this. There is no apparent pattern in your errors. You make errors, you typically make errors, but there is no specific pattern. You get it right, you are in the right direction, just that there is some variance. And then we have high bias and low variance, so your shooting is very consistent, but it's always wrong. That could be the picture. Very consistent. All the arrows go here. It's just that you always hit the wrong spot because you have a bias. Yeah, and then, well, high bias, high variance, that's then, if you wish, the worst situation. Maybe something you are always too high. But you also vary a lot in your inability to hit the target. That would be high bias and high variance. That's the way to look at it. And you can imagine that if bias is something like the error of your model, or if you translate it with the ability to reduce the error on the training sample, it makes perfect sense that a complicated model, a complicated neural network, has very low bias. So the problem with neural networks is high variance, which we need to control. And regularization is just the way to control this problem, where we add a penalty to our loss function that penalizes model complexity. More specifically, what we typically do in regression, but also in neural networks, we penalize large weights, large beta coefficients in regression, or large weights, connection weights in a neural network. We penalize that. And mathematically, we achieve this by adding this penalty function to our objective. Note the previous objective, J of W, that minimizes our loss on the training sample. That's also called here, this is called empirical risk minimization, empirical risk minimization, where to train a neural network we only emphasize the empirical risk or the empirical loss, the loss on our training data. And in regularization, we go away from that approach. We don't care about the empirical risk or loss only, and instead we add this penalty, the purpose of which is to penalize the complexity of the model, where we measure complexity by the sum, the absolute sum, or the squared sum of our model coefficients. And to appreciate that, you need to convince yourself that large weights are a sign or a trait of complex models. And then we need this hyperparameter lambda here typically, because now we have an objective to train our models that has two parts. One being the empirical loss and the other being the complexity. And we want to minimize both the loss on the training sample and the complexity of our model. But there is a trade-off between these two, right? If you have a model that is not complicated, then you will not be able to reduce your empirical loss to zero, or maybe you might not even succeed to reduce it a lot, because if the pattern in the data is complicated, a very simple model cannot pick up that pattern, right? So there is this trade-off, and lambda, which is a meta parameter that we have to set, allows us to control how much we emphasize empirical loss during training, reducing empirical loss, and how much we emphasize complexity, and how much we seek a model that has low complexity. And I'm sure you know the two popular ways to set these penalty function. Most popular ones are the L2, or also called the rich penalty, where we minimize the squared sum of all the weights. And then there is the lasso penalty, or the L1 penalty, where we minimize the absolute sum of all the weights. And maybe less known, because lasso and rich, they have respective merits and also demerits. There is no perfect choice. Because of that, there is a more advanced penalty called the elastic net penalty, which basically combines rich and the lasso penalty. Combining the two of them sounds like a good idea at first glance, because if they have different advantages and disadvantages, why not combining them? Good point. The main disadvantage of the elastic net penalty, if you look about it, it's yet more complicated. We have the parameter lambda that we had before, one meta parameter, but in elastic net we have a second meta parameter alpha, which governs the degree to which we focus on the L2 penalty and the L1 penalty respectively. So yet more meta parameters that we need to set, where we need to come up with good values that makes the tuning or the configuration of our neural network yet more complicated if we choose to use this penalty. So again, no free lunch. And what I like are these pictures here that I pulled from some nice blogs that you can read up if you wish, that try to showcase what these penalties really mean, or what happens if we add them to our loss function. So let's spend some time on these pictures. You see a two-dimensional space which is spanned by our two weights, W1 and W2. So we imagine a very simple model that has only these two free parameters, W1 and W2. That could be a regression model where we have two independent variables, for example. And indeed, I am also assuming that our loss, that J of W is square error loss, 1 over n sum I to n yi minus yi hat squared. And with this loss function, it's a squared function, right? So the functional shape of J will look somewhat like these red circles that you see in the picture. And these are meant to represent ISO cost lines. So on every combination of W1 and W2, on one of these lines, the loss J is the same. And let's imagine that the optimum, the minimal point of this loss function is here, right in the middle. Okay, so previously we called that Y star. Y star is the minimum of J with respect to W. That's the point of minimum loss, where we would set W1 to whatever this value might be, and we set W2 to, right, whatever that value may be. So this is W1 star, and this here is W2 star. And then, well, W star is just the vector of W1 star and W2 star. All right. Should make it look more like a vector. So this is the solution that we would typically use if we train our neural networks, or generally if we fit our model by empirical risk minimization. That would be the solution to a linear regression model estimated by OLS, the point where the loss is minimal. Right, and if we now add a penalty to our loss function to penalize complexity, this means that our optimum to the new loss function, J plus lambda times some penalty, will be somewhere else, right? The green ball or the green diamond in the lower picture, they are to represent the L2 penalty and the lasso penalty respectively. And if you think about the L2 penalty, let's start there, which is just the sum of W squared. It makes sense that this is a ball, right? It's just a squared function. It's centered at the origin, and it will have this shape. And now, if we minimize our augmented loss function, empirical loss plus penalty, then the optimal point would no longer be W star, as our penalty for a given lambda and a given set of weights, we would pick a solution, or we would need to pick a solution where our loss function, or the ISO cost curves corresponding to our loss function, and the penalty function, where they are tangent. So we are looking for a touch point, like this one here. Maybe I use a different color. And we could call that Y double star. A solution where W1 and W2 both have a much smaller value than in the previous optimal solution. Because of the penalty, we introduce this penalty function. We enforce that now the minimum of our augmented loss function balances these two objectives, and the result will be that the optimal point, the minimal point, will be somewhere where the empirical risk and the penalty are tangent to one another. That is the point. And this optimal point will typically always be at a point in this space where the weights are smaller compared to the solution when we only minimize the empirical risk. This is how to read these pictures. So W double star would be, the minimum over W of J of W plus lambda times the penalty. And what's quite interesting is the lower picture that shows us the L1 penalty, the absolute sum, and how this penalty looks like visually. And we see that because of this shape that we now minimize the absolute sum of W1 and W2, our loss function will always be tangent to the penalty at one of the corners. And that is interesting because at one of these corners, as the one highlighted in the picture, one of the weights, in our example, it's W1 double star is equal to 0. And the reason I find that interesting is that remember that our weights are the multipliers to the features in our modeling problem. So some feature would be multiplied with W1, which at the optimal point has a value of 0, meaning that this feature will be discarded. Effectively, the L1 penalty performs feature selection, because at the optimal solution, several of these weights W will be 0. And that has to do with the shape of this penalty function. And this is a big advantage of the L1 penalty. It implicitly performs feature selection, while the L2 penalty will not do that. It has no incentive to set weights to 0. The tangent point will be anywhere on this ball, and it might be for coincidence or out of coincidence that one of the weights will be 0, but typically this is not the case. The L2 penalty might shrink weights a lot so that some of the features get very small weights, receive very small coefficients, and then don't really matter much in the model predictions, but their weights won't be 0 with the L2 penalty. There is no feature selection, typically, and you can try that out empirically. You'll see how this is true. The advantage of L2 then, it's a squared function, and the function is easier to minimize numerically, as opposed to this absolute sum. What's the derivative of that, right? It's a bit more complicated. Okay, so there was regularization. And regularization is something you probably have seen in regression before. Well, you should have seen it in regression before. But it's used in neural networks as one mechanism to prevent overfitting. And now I want to look at some more specific measures to prevent overfitting from happening in neural network training. The first of which is early stopping. This means that when we train our network, we are holding back some data. We have our training data, we draw a sample from that training set. This sample is often referred to as the validation sample. It's not used for training. It is used to trace the error of our model during training. And remember, training a neural network is done by some iterative algorithm. Remember your backpropagation lesson. We train our network iteratively, and now we can trace how the loss develops with training iterations. And we do that on both the training sample, where the loss is guaranteed to decrease, and we also trace the loss on the validation sample, which is the blue line here. And then conceptually, at some point, the validation loss will start to increase again. First of all, It will decrease when the model is trained, the weights adapt to the data, the neural network picks up pattern in the data, so the loss decreases on both the training and the testing of the validation sample. But at some point, all the systematic patterns in the training data have been learned. These systematic relationships also exist in the validation sample, which was taken out of the training sample. And if we then continue training, if we then sort of force the neural network to further reduce training loss, the only way to further reduce training loss is to capture the noise in the training sample. And this is why the green line continues to decrease, although at diminishing returns, right? But the blue line does not. Now we are fitting noise in the data. Now we are learning noise. We are memorizing the training sample. And so the error on the validation sample increases because this noise that is now modeled just does not exist in the validation sample. And therefore the error increases on the validation data, and this indicates that we should stop training our neural network. We should not train it any further, but stop training whenever we observe the validation error to increase. That is called early stopping. It was invented in the scope of neural network training. Nowadays, some other machine learning algorithms also give you a way to prevent overfitting by early stopping. Gradient boosting, for example, or XGB has an option to do that. And it's just yet another measure to protect your network against overfitting. The problem with that in practice is that the development of the training and the validation loss, normally it does not look as nicely. It's a much more erratic function. If you look at it, it's much more like that, and then there will be some bumps, and then it's a bit harder to tell where actually is the point at which you want to stop your training. That's a more practical problem. And in fact, you can check that out on TensorFlow. I'm talking about the TensorFlow playground here, right? Okay, so that was simple. Let's move on. Something that came out more recently is Dropout. Dropout means that you take your neural network architecture and you randomly set certain computational units to 0. You drop them out with some probability. These dropout rates are a metaparameter. They're often set to 50% by default, and this default works okay. It's a metaparameter, so you might want to consider tuning this metaparameter when you build a neural network. Anyways, you apply dropout to one layer. Any layer in your neural network, but the output layer. No dropout at the output layer, that would not make any sense. You apply that to the hidden layer. You can also apply dropout to the input layer, or some people call that the visual layer, where you see some data, meaning that you knock out certain features in your data. That's also possible. If you apply dropout to the visual layer, however, then typically you pick a lower dropout rate. So for P input, you would typically, well, e.g. 20%. You would not go much larger than 20%. Otherwise, you would knock out too many of your features that you believe to have an impact, right? So, it's an operation that you apply to layers of your neural network. And it means that you randomly deactivate some of the nodes in the respective layer, as you see here in this example. And what that means in turn, if you deactivate nodes, it means that all the weights on the incoming and outgoing connections of the dropped out node are effectively set to 0, or they are also dropped out. And that is relevant when you train your neural network, because remember backpropagation. When you train your neural network, you measure the loss at the output layer, And then you backpropagate that loss through your network back to all the weights in the network, layer by layer. And when we talked about backpropagation, we've been examining these computational graphs that remind us how the partial derivatives are calculated in the scope of backpropagation. And now if we have dropped out a unit, then that affects the computational graph. It just changes. So all the weights that are currently depicted with these very thin lines, they do not exist anymore. They are dropped out, and therefore the partial derivative, the way these are calculated, that changes. To tune a certain weight, let's say tuning this weight here, that would be W, say that's W2, 1. Oh, sorry, that's a bad example. Apologies. Tuning this weight here at the input layer, W1, 2, we would normally look at the computational graph and all the connections that affect this weight. So normally, in theory, we would also consider this connection here that goes into the corresponding hidden unit in our computation of the partial derivative. But now this connection, it just dropped out. So we would not consider it anymore. And therefore, our gradient update changes. We only consider the gradient for the remaining connections after dropping out certain nodes in the network. That is the idea. Or well, that's not the idea, but that is what effectively happens. And then we could start to reason why this might be a good idea. And as a matter of fact, if you read this paper by Srivastava and colleagues, there is a lot of theory underneath, and much more theory was developed after the publication of that paper, so that we nowadays have a very good understanding of why dropout is a good idea. And I want to give you a brief introduction to this. The thing is that in backpropagation, one possible problem is that hidden nodes basically co-adapt to one another. You could think of that as one node, maybe this node here, that during training it learns to correct some of the errors that another node is making. Maybe that node here. This is meant by co-adaptation. The weights are trained such that these two nodes that I have just highlighted operate together. They collaborate, which sounds nice. Collaboration is good. We like teamwork in general. However, in neural network learning, that's not so beneficial. You rather want to have the hidden units to capture some patterns in the data that are useful in their own right. You want them to capture patterns that are generally useful. And you want that for each of your nodes in the neural network. Otherwise, you might not need the node at all. And dropout encourages this behavior that the units learn patterns that are generally useful, because due to dropout, a single unit cannot rely on the output of previous units in the neural network, as these previous units might be dropped out. So you sort of train the network, you train a network of more egoistic units, if you wish, where everyone tries to perform a task that is beneficial without relying too much on the other units in your neural network. Or another way to look at it would be to say you train your neurons so that they must perform well in a wide variety of different contexts, whereby the context is then provided by the other hidden units and whether they are there or whether they are not there because of dropout. That's some intuition of why dropout works, in that it gives an incentive of learning patterns that are robust. And robustness is beneficial when you apply your neural network to novel data. Robustness is beneficial for generalization. And another way to look at dropout, which is quite interesting, is that if you train your neural network, then you do train it over basically a set of architectures. This is what I'm trying to show here on the left-hand side. You do train a neural network where you only have the hidden unit Z11 because of dropout, but you also, in parallel, you train a neural network where you only have the hidden unit Z12. And of course, these are very simple pictures. If you imagine a large neural network, it would be more explicit. How you train your neural network over a variety of different architectures. And that's quite useful because it means that you are effectively creating some sort of ensemble of different neural network architectures. And just to note, due to this behavior, you will typically need to scale your weights when you put it into production, the neural network. The weights trained, or the weights that result from training the neural network with dropout, they will be larger compared to training the neural network without dropout, and that is typically addressed by adjusting the weights when you put the network into production. So for example, I put this W divided by 2 here. If I train my neural network with a dropout rate of 50%, then what would happen in production, and this is something that your deep learning library will do automatically for you, the corresponding connection weight will just be halved. So you don't really get to notice that a lot, but just bear it in mind that because of other nodes being dropped out, the weights of the hidden units and of the connections are typically a lot larger, and we address that by scaling down the weights when we put the network into production. And as a final remark, there is some very interesting research that examines how dropout gives us a way of approximating Bayesian learning of a neural network, and how we could obtain in a very cheap manner uncertainty estimates from a neural network trained by means of dropout. We can't go into the details of that, but if you are interested and maybe have some previous insight into Bayesian statistics or even Bayesian deep learning, I can highly recommend this paper, Dropout as a Bayesian Approximation. In a nutshell, if you effectively train your neural networks over many different network architectures because of dropout, so the different architectures come from dropout, and you train your neural network over all these architectures, why doing that only during training? Why not also using these different architectures that you implicitly have trained simultaneously during predictions? And instead of producing one forecast for a single data point, why not let all these different network configurations that you have visited during your training, why not letting them all cast a vote on the data point that you try to predict? And that means that from this way of applying the neural network, normally dropout happens during training, but if you also use it during application, when you produce forecasts, you could get one forecast from each one of the different network configurations, or from the different network architectures. This means you create an ensemble forecast. And you get this for free. You do not need to train multiple neural networks. You sort of get it for free because you have used Dropout. And then in this paper and subsequent paper, the colleagues analyze the behavior of these ensemble forecasts and the extent to which they give you an understanding of the uncertainty that is associated with forecasts. And normally, these estimates of uncertainty are a key advantage of Bayesian statistics and Bayesian deep learning. And intuitively, that makes sense. Let's say you want to predict some stock price, and your model tells you that tomorrow's closing price is 1,560. 1,560, that's very useful if you know that today the closing price is 1,400. That would be a substantial improvement or increase of the price, so you might want to buy this stock. But how much more informative would it be if you had an understanding how certain, how confident the network is in this prediction? And that is where uncertainty estimates that you could maybe depict as these shaded areas that you see here that surrounds predictions, where they are highly useful. Uncertainty estimates in general are highly useful for decision making if you want to act on your forecasts. Normally, you need to learn your networks in a Bayesian manner to get these, which is very costly computationally. Bayesian deep learning has the disadvantage that it doesn't scale as well as the standard frequent shifts approach. And Dropout is a way to get uncertainty estimates for free, or essentially for free. That sounds great. Now note that there is also research that adopts a more critical perspective than Gal and Rahmani, apologies, difficult name for me. And there is also research comparing the quality of these uncertainty estimates. And when you then compare Dropout uncertainty estimates to those that you get from proper Bayesian methods like MCMC, the latter do perform a lot better. But, well, you get some notion of uncertainty at least, which is useful. Or a nice byproduct of Dropout. Remember the key point of Dropout for us is to prevent overfitting by setting to 0 some of the hidden units randomly in a layer, which prevents the hidden units from co-adapting to one another and learning some more generally useful patterns. And we effectively average over many network architectures when we generate forecasts. So we are doing an ensembling, which we know to reduce variance. Ensembles always reduce variance and therefore achieve a better trade-off between bias and variance, since they've reduced variance. So that's intuitively beneficial. And this is how Dropout prevents overfitting. Some cautionary notes. If you can drop out certain nodes in your neural network, you change the architecture and you also reduce the capacity of your neural network. You limit its ability to capture highly complicated patterns in data. And you also introduce some noise. Long story short, you will often find that you need to train your network a little longer. So allowing for more epochs to train your network. Remember, one epoch was one path through the entire training sample. It's often a good idea to let the neural networks train more epochs if you use Dropout. Or else you might consider higher learning rates. But it depends a little bit on the training algorithm that you are using. Adam might behave a little bit different than RMS prop or yet another one. But bear in mind that there clearly is dependency between the training and Dropout as Dropout changes the architecture. And by the way, if you wonder, okay, I understood that Dropout knocks out certain nodes during training, when exactly does that happen? Well, it happens anytime you update the weights in your neural network. every time you're doing a gradient step, dropout comes into play. Prior to doing the gradient step, you calculate the gradient, and when you do this, you consider which connections do actually exist in my neural network at this step, considering those nodes that have been dropped out. So if you train your network using batch gradient descent, you would basically drop out some nodes, then you train your network for one epoch, and then for the next epoch, you would randomly sample a different set of nodes per layer that get dropped out. That is what happens in batch gradient descent. In stochastic gradient descent, on the other hand, you would take one example, calculate the loss, approximate the gradient using this single data point, and then when you backpropagate for this single data point, when you approximate the gradient, you would consider the network architecture. And for the next data point, because you do an update with every data point in stochastic gradient descent, you would basically randomly sample a different set of nodes that you drop out, every time doing this per layer. So in a nutshell, the sampling of nodes to drop out, that happens with every weight update, meaning once for the whole training sample, once per epoch in batch gradient descent, once for every data point in stochastic gradient descent, and once for each mini batch in mini batch gradient descent. That is how it works. And that also concludes our journey into dropout and the means to prevent neural networks from overfitting.